Hello and welcome everyone. My name is Milko Mitropolitsky and today I'm going to present to you our work called Graph Representation Matters in Device Placement, which was done at KTH in Stockholm. To begin with, let me walk you through the agenda for this presentation. First, I'm going to outline the device placement problem that we're trying to solve. Next, I will describe what are our contributions, followed by the achieved results. We wrap up with some conclusions. I hope you enjoyed the presentation and let's jump in. Modern neural networks are required to perform increasingly complex tasks. That is why more data and more parameters are needed to keep up with the demand. By increasing in size, the neural networks can reach a point where they cannot fit on a single machine. In these cases, scaling by model parallelization becomes de facto a must. Model parallelization means that the neural network model is split into smaller parts, with each part placed on a different device. All devices work on the same batch of data, and the output of each part of the model is combined to provide the input to the next step. By using this approach, the model can also take advantage of different hardware components. There's the obvious negative of communication and synchronization overhead. Furthermore, model parallelization is hard to implement, as it requires additional work to be done for each model, and there is no one-size-fits-all solution yet. So, how do we automate the process of device placement in model parallelization? More concretely, we're trying to understand how the different parts of a model should be distributed in such a way that the runtime of the distributed model is minimized. This is what we call the device placement problem. To give a rudimentary example, we see this neural network represented as a graph. The graph nodes represent NN operations. The numbers represent which device an operation is placed on. What we want to achieve from this is an automatically generated distributions of operations, like the second picture, and hopefully it has optimal runtime. The current solutions that try to solve the device placement problem have a few common traits. They represent neural network models as graphs. They use some grouping of NN operations into nodes to reduce graph sizes. They use some sort of graph embedding, and finally they use reinforcement learning to produce placement policies. Place2 was, at the time of writing this research, the current state of the art in device placement. It had the best results in runtime execution, which is the time it takes to execute a model. And on top of that, it was also the first solution able to generalize to previously unseen models. The authors have used an RL agent, which outputs a per node placement. Each epoch, which is one iteration over one neural network, all of the input graph nodes are passed through the system iteratively. The current node goes through a graph embedding neural network, which allows for the generalizability, and then through a policy network, which produces a device classification for that node. Finally, the runtime of the updated graph is simulated and is used as a reward to the RL agent. The runtime is used as a reward to update the internal neural network's gradients for the next node. Our main contribution is that we explore the impact of different graph embedding architectures on device placement runtime. In practice, we use Place2 as a base and replace the graph embedding module of Place2 with two other graph embedding architectures, GraphSage and PGNN, and measure the quality of the produced placement policies. First, let's take a look at our baseline graph embedding architecture, Place2. By baseline, we mean that we compare all of our results for the other architectures to the results achieved by Place2. So, this is our neural network represented as a graph. Each node has a set of features: total runtime, output size, current placement, is node current, and is node done. Place2 is a GNN approach, and as such works by aggregating information of the node's neighbors in some way using message passing. What this gives us is a set of parent nodes, a set of child nodes, and a set of parallel nodes in relation to the current one. The set of parent nodes contains every node that has an incoming path to the current node. Child nodes are nodes that can be reached from the current node, and parallel nodes, lastly, cannot be reached from the current node via the edges of the graph. Finally, these sets are combined together with the current node and are passed to the policy network, which outputs a device placement. Now we take a look at our first implementation, GraphSage. The initial graph is similar, as are its features. What is different is how the neighborhood is aggregated. First, a neighborhood embedding is generated. A neighborhood embedding encapsulates the information about neighbors 2 hops away from the current node. In this example, we start from the single node at the bottom. Since it is located 2 hops away from the current node, its embedding is its own feature information passed through a simple 3-layer neural network. Next, the dark blue node is one hop away from the current node. To get its embedding, we take the aggregated embedding of its child nodes, in this case, the embedding of the light blue node, and concatenate it with its own. The final embedding of the current node is achieved by concatenating the current node's feature embedding with the aggregation of the embeddings of its neighbors. A device placement is suggested afterwards. The next architecture, we test this position-aware GNN or PGNN. It adds locality to the graph embedding, which allows us to distinguish if two nodes with similar neighborhoods are located at different parts of a graph. This is done by adding anchor sets of nodes. Of course, our implementation starts with the same graph. First, we generate the embedding of the current node by using the graph sage method we just presented. We then add randomly chosen anchor sets. The embedding is generated by calculating the relation of the current node to each anchor set. Namely, we combine the aggregation of the anchor set with the embedding of the current node. That combined vector is multiplied with the distance between the current node and the anchor set. We do this for each anchor set, and the final node embedding of the current node is the combination of all those things. We evaluate our experiment using two metrics. The first one is execution time improvement. How much faster is a placement according to the new policy than the initial single device placement according to the place-to simulator. The second one is computation time, which means how much time it took the system to achieve these runtime improvements. Our experiment setup is as follows. We have 3 different data sets. We pass all of them through the system and repeat it for all architectures. We simulate placement on 3, 5, and 8 devices. The initial placement is on a single device, similar to what we see here. After the system has finished, we expect to see different placements, similar to what we see now. We measure execution time improvement compared to the initial placement as measured by the place-to simulator. We also measure the computation time required by the system to reach the result. Finally, we use the results achieved by place-to as a baseline. Here, we see the average execution time improvements for each graph embedding architecture on each data set compared to the initial placement. On the x-axis, we see the 3 data sets, and for each the 3 graph embedding architectures, place-to in blue, graph sage in red, and PGNN in yellow. On the y-axis, we have the execution time improvement measured in percents. We see that place-to achieves a good result of 25.1% average from all data sets. Graph sage reaches a similar 25.4 execution time improvement. And lastly, we see that the added locality in PGNN has a positive impact on the execution time of placement policies, as it achieves the largest average improvement of 31.2% across all data sets. Here, we see the average computation time per epoch for each graph embedding architecture in each data set. Again, as the previous slide, the x-axis, we see the 3 data sets. For each data set, the 3 graph embedding architectures. The y-axis represents the average time required to finish a 20 epoch experiment measured in seconds. The first thing we observe is that the computation time depends on the size of the data set. PTB has the largest average computation time across all techniques, as it has the biggest average number of nodes per instance. It is evident that the added locality of PGNN comes with additional computation cost. PGNN has the slowest average computation time of 173 seconds. On the other hand, graph sage is significantly faster than place-to with 143 seconds against 162 seconds for place-to. In conclusion, we can say that graph embeddings can have an impact on both runtime improvement and computation time for device placement. We see that in regards of execution time improvement, our graph sage implementation performs only 1% better than the place-to baseline. PGNN, however, achieves almost 24% better results than place-to. Adding locality to the graph embedding produces better runtime improvement, but the additional complexity comes at the cost of longer computation time. In terms of computation time, we observe that the graph embedding architecture complexity has an impact. Graph sage is 11% faster than place-to, and the added locality of PGNN makes it almost 7% slower. This concludes my presentation, and thank you for the attention.